In military munitions, a fuse, sometimes fuse, is the part of the device that initiates function. In some applications, such as torpedoes, a fuse may be identified by function as the exploder. The relative complexity of even the earliest fuse designs can be seen in cutaway diagrams. In military munitions, a fuse, sometimes fuse, is the part of the device that initiates function. In some applications, such as torpedoes, a fuse may be identified by function as the exploder. The relative complexity of even the earliest fuse designs can be seen in cutaway diagrams. Artillery fuses are tailored to function in the special circumstances of artillery projectiles. The relevant factors are the projectile's initial rapid acceleration, high velocity, and usually rapid rotation, which affect both safety and arming requirements and options, and the target may be moving or stationary. Artillery fuses may be initiated by a timer mechanism, impact, or detection of proximity to the target, or a combination of these. Hand grenade fuse. Requirements for a hand grenade fuse are defined by the projectile's small size and slow delivery over a short distance. This necessitates manual arming before throwing, as the grenade has insufficient initial acceleration for arming to be driven by setback and no rotation to drive arming by centrifugal force. Aerial bomb fuse. These are also referred to as pistols. The main design consideration is that the projectile is large and accelerating vertically downwards and may or may not be rotating relatively slowly. Landmine fuse. The main design consideration is that the bomb the fuse is intended to actuate is stationary, and the target itself is moving and making contact. Naval mine fuse. Relevant design factors in naval mine fuses are that the mine may be static or moving downward through the water, and the target is typically moving on or below the water surface, usually above the mine. Fuse categorization by activation mechanism. Time fuse. Time fuses detonate after a set period of time by using one or more combinations of mechanical, electronic, pyrotechnic, or even chemical timers. Depending on the technology used, the device may self-destruct, or render itself safe without detonation, some seconds, minutes, hours, days, or even months after being deployed. Early artillery time fuses were nothing more than a hole filled with gunpowder leading from the surface to the center of the projectile. The flame from the burning of the gunpowder propellant ignited this fuse on firing, and burned through to the center during flight, then igniting or exploding whatever the projectile may have been filled with. By the 19th century, devices more recognizable as modern artillery fuses were being made of carefully selected wood and trimmed to burn for a predictable time after firing. These were still typically fired from smoothbore muzzle loaders with a relatively large gap between the shell and barrel, and still relied on flame from the gunpowder propellant charge escaping past the shell on firing to ignite the wood fuse and hence initiate the timer. In the mid to late 19th century, adjustable metal time fuses, the forerunners of today's time fuses, containing burning gunpowder as the delay mechanism, became common, in conjunction with the introduction of rifled artillery. Rifled guns introduced a tight fit between shell and barrel and hence could no longer rely on the flame from the propellant to initiate the timer. The new metal fuses typically use the shock of firing, setback, and slash or the projectile's rotation to arm the fuse and initiate the timer, hence introducing a safety factor previously absent. During World War I, mechanical, or clockwork, time fuses were introduced for artillery by Germany, and some variants are still in use. As late as World War I, some countries were still using hand grenades with simple black match fuses much like those of modern fireworks. The infantryman lit the fuse before throwing the grenade and hoped the fuse burned for the several seconds intended. These were soon superseded in 1915 by the Mills bomb, the first modern hand grenade with a relatively safe and reliable time fuse initiated by pulling out a safety pin and releasing an arming handle on throwing. Modern time fuses often use an electronic delay system. Impact fuse. Impact, percussion, or contact fuses detonate when their forward motion rapidly decreases, typically on physically striking an object such as the target. The detonation may be instantaneous or deliberately delayed to occur a preset fraction of a second after penetration of the target. An instantaneous superquick fuse will detonate instantly on the slightest physical contact with the target. A fuse with a graze action will also detonate on change of direction caused by a slight glancing blow on a physical obstruction such as the ground. Impact fuses in artillery usage may be mounted in the shell nose, point detonating, or shell base, base detonating. Proximity fuse. Proximity fuses cause a missile warhead or other munition, e.g. air-dropped bomb or sea mine, to detonate when it comes within a certain preset distance of the target, or vice versa. Proximity fuses utilize sensors incorporating one or more combinations of the following: radar, active sonar, passive acoustic, infrared, magnetic, photoelectric, seismic or even television cameras. These may take the form of an anti-handling device designed specifically to kill or severely injure anyone who tampers with the munition in some way, e.g. lifting or tilting it. Regardless of the sensor used, the preset triggering distance is calculated such that the explosion will occur sufficiently close to the target that it is either destroyed or severely damaged. Remote detonators. Remote detonators use wires or radio waves to remotely command the device to detonate. Barometric fuse. Barometric fuses cause a bomb to detonate at a certain preset altitude above sea level by means of a radar, barometric altimeter, or an infrared rangefinder. Combination fuse. A fuse assembly may include more than one fuse in series or parallel arrangements. The RPG-7 usually has an impact, PIBD, fuse in parallel with a 4.5 second time fuse, so detonation occurs on impact, but not later than after 4.5 seconds. Military weapons containing explosives have fusing systems including a series time fuse to ensure that they do not initiate, explode, prematurely within a danger distance of the munition launch platform. In general, the munition has to travel a certain distance, wait for a period of time, via clockwork, electronic or even a chemical delay, or have some form of arming pin/plug removed. Only when these processes have occurred will the arming process of the series time fuse be complete. Mines often have a parallel time fuse to detonate and destroy the mine after a predetermined period to minimize casualties after the anticipated duration of hostilities. Detonation of modern naval mines may require simultaneous detection of a series arrangement of acoustic, magnetic, and/or pressure sensors to complicate mine-sweeping efforts. Fuse safety/arming mechanisms. The multiple safety/arming features in the M734 mortar fuse are representative of the sophistication of modern electronic fuses. Safety/arming mechanisms can be as simple as the spring-loaded safety levers on M67 or RGD5 grenade fuses, which will not initiate the explosive train so long as the pin is kept in the grenade, or the safety lever is held down on a pinless grenade. Alternatively, it can be as complex as the electronic timer countdown on an influence mine, which gives the vessel laying it sufficient time to move out of the blast zone before the magnetic or acoustic sensors are fully activated. In modern artillery shells, most fuses incorporate several safety features to prevent a fuse arming before it leaves the gun barrel. These safety features may include arming on setback or by centrifugal force, and often both operating together. Setback arming uses the inertia of the accelerating artillery shell to remove a safety feature as the projectile accelerates from rest to its in-flight speed. Rotational arming requires that the artillery shell reach a certain RPM before centrifugal forces cause a safety feature to disengage or move an arming mechanism to its armed position. Artillery shells are fired through a rifled barrel, which forces them to spin during flight. In other cases, the bomb, mine or projectile has a fuse that prevents accidental initiation, e.g. stopping the rotation of a small propeller, unless a lanyard pulls out a pin, so that the striker pin cannot hit the detonator even if the weapon is dropped on the ground. These types of fuse operate with aircraft weapons, where the weapon may have to be jettisoned over friendly territory to allow a damaged aircraft to continue to fly. The crew can choose to jettison the weapon safe by dropping the devices with safety pins still attached, or drop them live by removing the safety pins as the weapons leave the aircraft. Aerial bombs and depth charges can be nose and tail fused using different detonator/initiator characteristics so that the crew can choose which effect fuse will suit target conditions that may not have been known before the flight. The arming switch is set to one of safe, nose, or tail at the crew's choice. Base fuses are also used by artillery and tanks for shells of the squash head type. Some types of armor-piercing shells have also used base fuses, as have nuclear artillery shells. The most sophisticated fuse mechanisms of all are those fitted to nuclear weapons, and their safety/arming devices are correspondingly complex. In addition to PAL protection, the fusing used in nuclear weapons features multiple, highly sophisticated environmental sensors, e.g. sensors requiring highly specific acceleration and deceleration profiles before the warhead can be fully armed. The intensity and duration of the acceleration/deceleration must match the environmental conditions which the bomb/missile warhead would actually experience when dropped or fired. Furthermore, these events must occur in the correct order. Note, some fuses, e.g. those used in air-dropped bombs and landmines, may contain anti-handling devices specifically designed to kill bomb disposal personnel. The technology to incorporate booby trap mechanisms in fuses has existed since at least 1940, e.g. the German ZUS-40 anti-removal bomb fuse. Reliability. A fuse must be designed to function appropriately considering relative movement of the munition with respect to its target. The target may move past stationary munitions like landmines or naval mines, or the target may be approached by a rocket, torpedo, artillery shell, or air-dropped bomb. Timing of fuse function may be described as optimum if detonation occurs when target damage will be maximized, early if detonation occurs prior to optimum, late if detonation occurs past optimum, or dud if the munition fails to detonate. Any given batch of a specific design may be tested to determine the anticipated percentage of early, optimum, late, and dud expected from that fuse installation. Combination fuse design attempts to maximize optimum detonation while recognizing dangers of early fuse function, and potential dangers of late function for subsequent occupation of the target zone by friendly forces or for gravity return of anti-aircraft munitions used in defense of surface positions. Series fuse combinations minimize early function by detonating at the latest activation of the individual components. Series combinations are useful for safety arming devices, but increase the percentage of late and dud munitions. Parallel fuse combinations minimize duds by detonating at the earliest activation of individual components, but increase the possibility of premature early function of the munition. Sophisticated military munition fuses typically contain an arming device in series with a parallel arrangement of sensing fuses for target destruction and a time fuse for self-destruction if no target is detected.
Please subscribe and thanks for watching.